Okay. Well, good evening. It's starting to rain, and we're all stuck together trying to get through this material. I'm going to do four slides, I think, that I didn't cover last week because they do show up in tonight's material. One of the functions that are very integral to radio is a thing called a filter. And I don't think filters are that obvious a thing, but there are different kinds of them. So I'm going to show you some stuff about them. And then this is more I'm trying to give you a bigger picture here. Anyway, in G7 and also G7D, these are specific questions that ask questions like a low pass filter cutoff, ultimate rejection, pass band, upper and lower power points. So let me show you this on these filters. All right, the bottom, I didn't actually put the axis. The bottom axis over here where it says low pass or high pass, that is frequency. So let's say this frequency range starts from 0 and it goes up to say 10 megahertz over here at this point, say. And so what this low pass filter does is it rejects everything that's where it's 0 over here. So it's basically going to reject any frequencies greater than 10 megahertz if this were 10 megahertz over here. So it rejects those, which means that it passes all the other ones. So anything below 10 megahertz goes through the filter and comes out the back. So this is a black box where you put in some frequencies and you determine how much of those frequencies come out, or how many, which ones come out, which ones don't come out. And
it's like a guardian.
It's right? Like a guardian. Now you see typically there's a flat spot in a filter, like the top of this, or the top of here, or the top of this, or the bottom of this. Yeah. That flat part is called a pass band. That's the area where the frequencies come through this filter. Where it's 0 is where they're all rejected. Now, there's always a transition region from the flat part to the 0 part, which doesn't just chop off like a square. It's always rounded. And what that means is that in this point, everything that comes in comes out exactly the same size. But as this goes down and it starts to reject, things that come in at this frequency, say this was 10 over here, this is like 5 in the middle, that frequency comes out, but it comes out at a fraction of what it was came in. So it could be like half comes in. So in this transition region,
power?
By power or voltage. Say it was 10 volts and it came in at 10 volts and it went out at 10 volts in this range, where over here it might come out as 5 volts. Until you get to, then as you get higher in frequency, less and less of that frequency comes through until eventually there's nothing that comes through. Follow that? Now,
so it only
sounds like a flim flam.
I'm sorry, what was that, Pat? I mean, Nolan?
It sounds like a flim flam.
Well, filters can be very complicated beasts, but they also are not that complicated at this level. Okay. There is one magic point, though. What people do is, see where this turns off over here? Well, the point at which the signal that comes out is a little smaller than the one that's up the top. When it gets to be half, that's called a 3 dB point, or half the power. So you'll see in question G7D14 has an answer of upper and lower half power in a bandpass filter. So look at this bandpass filter. What it does is it lets frequencies from here to here go through. So let's call the flat part like maybe I don't know, 3 megahertz to 5 megahertz. So this is like 3 to 5. So down here, we got like maybe 2 megahertz. And there's a point where half of the power comes out. And that's called the 3 decibel point or the 3 dB point. In a bandpass filter, there's 2 of them. There's one over here on the low end, and there's one over here on the high end. In a low pass filter, there's only one, because everything's flat until it gets to the point where it's half. And then in the high pass filter, this rejects all the low frequencies. So anything like 0 to 5 megahertz would never come through. But then there's a point where all the high frequencies go through. And in this transition region here, there's a point where it's half, and that's called the 3 dB point. So a bandpass filter has upper and lower half power points. A low pass filter and a high pass filter only have one. And a band stop filter, I don't think they even talk about band stop filters in the test, but a band stop filter is the 4th kind, and that's where everything gets rejected in the band pass or in this area, and everything else goes through. And this has 2 3 dB points as well, here and here. So I put frequency at the bottom here. So this is frequency. In this case, up means gain. That is, there's something that comes out. If you go down, it means loss. So when the loss is infinite, that means nothing comes out. And I don't want to deal with all of the logarithms associated with how we draw these, but basically these are the 4 kinds of filters. So low pass has 1 cutoff frequency. My hint for G7 D13 is that the question has the word reject in it. So the answer is ultimate rejection. So that's just I think that's a silly question, but anyway.
Hope I get it.
If you get it, the question has reject in it and the answer has reject in it. Whoops, sorry. There we go again with the stupid thing in my way. Okay. G17 has a thing called insertion loss as a word. The answer is passband loss or gain. What insertion loss means is this flat line here, you can think of it as 1. That is, if whatever comes in goes out. So if I put 10 volts in the low pass region where I'm not rejecting, I put 10 in, I get 10 out. That has a gain of 1. In other words, whatever I put in comes out. That means gain is 1. If I have it designed so, and I might want to design it so I don't get all of it out. I may want to put in 10 and get 5 out. If I put in 10 and I get 5 out, that's a loss. In other words, that loss is called the insertion loss. It means if I insert something and I get less out, I've got a loss. If I put in 10 and I get out 50, that's a gain. So, and you can get gain by building an amplifier into the filter or after the filter. So insertion loss is called loss, but it might actually be in negative. That is, it might be gain. It's kind of a silly, we have a lot of, this has been a subject of a lot of discussion. Why do we call something loss when it can be big or small? You know, or why do we call it gain if it can be big or small? So if it's negative dB gain, it's loss. This has to do with the negatives and positives. But the only word that they care about in the thing is the word insertion loss. So these filters, there's a lot of material here. Filters get used by all kinds of things. They're all over the place in radios. They're useful for all kinds of things. I'll give you an example. Suppose you want to reject everything but the station you want to listen to, right, on your radio. Well, what filter would you use to get rid of everything but what you want to listen to? What kind? You want to get rid of everything except the station you want to listen to. What kind of filter would you use for that? Think about that. I got a station at in the 80-meter band at 3.9 megahertz. What kind of
Band
filter
stop.
would I use to get rid of everybody else?
The high pass.
I
Band
could, but
pass.
that's not the best answer.
And pass.
Band pass. So that everybody below me and everybody above me gets thrown out.
Ah,
And if the station's at 3.9 megahertz, where would the middle of the pass band be? Where would I
One
like the
point.
middle of the pass band to be? The signal that I'm
The
receiving is
3 dB.
a good guess, but no.
show off.
The middle of the pass band should be 3.9 megahertz, the way you have the desired signal. The signal should you want to center the pass band to be right where you want the stuff that you want to come through.
Oh,
The 3 dB stuff has to do with the fact that you can't make a perfect filter. It would be great if you could make a filter that was like flat over here and like nothing everywhere else. That would be ideal. In other words, the 3 dB point would not even exist. It would be like whatever it is in the middle and then nothing, everything else. Get rid of everything right on the edge. You cannot build a filter that way. It's impossible to build. So there's always some transition region where it goes from the middle of in the pass band, could be low, could be high, could be band pass, wherever the passing part is, there's always some transition to go to nothing. In fact, some filters, they never go to nothing. This thing that I say is zero over here is ideal as zero. Always, most filters, something comes out, even if it's been attenuated a significant amount. So that's what filters are. There's quite a bit of filters on it. Here's some actual circuits of filters. I mean, we talk about low pass filters. What do they actually look like? Well, here's a simple low pass filter right here. I'm sorry, high pass filter. I got it wrong. I did it the other way around. I made a high pass filter over here, then adjusted it here. It's just a capacitor and a resistor. This looks like a voltage divider, doesn't it? For all you voltage divider fans like me, this is like a voltage divider where this capacitor is there instead of the resistor. So I can make a filter out of a voltage divider. And I love voltage dividers, so I keep hopping on voltage dividers.
Why would anybody want to?
Because they want to make, well, let me do this. So here's a high pass filter that's adjusted so that it transitions at this frequency. Now this is a low pass filter. I just moved the capacitor. I just swapped the resistor and the capacitor. And now this only passes low frequencies, but I moved it higher than the high pass frequency. If I put these two filters together, what do I get? I get a band pass filter.
Yes, you do.
See that? So I could make a band pass filter by making a really good high pass and a really good low pass and put them together. And that's kind of what it does. If you want all kinds of information about that, you can go to this all about circuits thing. You don't need that for the test, but I give you references to find out everything you want to ever know. So I love putting these things out because they're voltage dividers. You can't get enough voltage dividers for me. All right, anyway. Okay, so I'm going to skip the next slides, but they are in a presentation. And I really want to tell you because what I did for the extra class folks is I did a detailed step-by-step computation for a low-pass filter. And we need all these magic terms like capacitive reactance and impedance and voltage and current. So I'm just going to go through these slides quickly. Here's our low-pass filter over here. See it? See the shape?
Mm-hmm.
Yeah. Okay. I calculated the red point and the green point. The angle is the green part and the red point is this insertion loss thing. You see this scale over here? The scale is, instead of being 1, 2, 3, like 10 megahertz, it's set up 0.1, 1, 10, 100, every multiple of 10. It's very often drawn, a filter is often drawn this way with this type of scale because there's so many frequencies that it's hard to show them on a simple linear scale like this. So this picture and the bottom picture is exactly the same picture. The red line and the red line are the same thing, but you can see much better what's going on with this kind of scale. Now, I calculated this red point and this green point, which is the same as this red point and this green point, in a big table where I figured out all of the individual impedances of all of the different parts. And I did the line that's red, okay? And someday when you're really good at this, I suggest that you try to calculate line 14.85 and see if you get the numbers that I get. So here's the step-by-step. I'm not going to do this. I'm just showing you that I put step-by-step instructions. I gave you a table to figure out yeah, go ahead, Pat.
On this picture,
Yeah.
are these 3 filters or are these something else?
Raise it a little bit so I can see what you, no.
Oh, sorry.
Okay, no, okay, I'll go back. This one. Oh, that's a good question.
3 filters?
Yeah, no, they're not.
Just the red one.
Just the red one. Now the red one, but there is something to the green one. The red one is how much, if I put 10 volts in and I get something else out, that's what the red one represents. So down here, if I put 10 volts in, I get 10 volts out. Over here, here's the 3 dB point. Okay? And I get half as much out. Now, what else happens is, remember that this is something that's going up and down, up and down, up and down, right? This is a frequency, right? When I get something out, it shifts in time a little bit because it takes time for it to go through the filter. So there's 2 things that you have to know about the output of a filter. How much the signal is attenuated, that is how much magnitude of it comes out, and also how much shift there is between the input and the output. The green line is the shift. And I even forgot what the blue line is. What's the blue line?
It's got a vector.
Yeah, it is a vector. It is a vector. So if I put in a signal at the beginning of my filter, and let's say it's 10 long and it's pointing in this direction, flat. Okay.
Yeah.
When it comes out, it's going to be at some other size. It's going to be maybe smaller or bigger, but it's also going to be rotated. And the green line says how many degrees of rotation the filter how much the filter shifts the output from the input. So a filter actually does 2 things to a signal. It shifts it and it changes its magnitude. Okay, so I didn't talk about that in the other picture, but that's what the green and red. Thank you for asking that question. The blue line is the amount of power that comes out because I multiplied current times voltage here. That's not too important for this discussion. Now, so I did this red line, and someday when you really feel ambitious and you want to look at this over, you try to calculate what's inside this blue ellipse for fun. But I wouldn't do it before this exam because it's not critical to the general. So I gave you all this data and it's there for fun. Okay. All right. This is stuff on the extra class. Okay. Then there's a bunch of questions on software defined radio. Anybody has, is that a new term for you folks?
Software defined radio?
Software defined radios.
That's new.
Okay. Well, first of all, they said, what is in G7 C11? They said, what's an SDR? What's a software defined radio? A software-defined radio is a piece of equipment that processes radio signals, things that vibrate in time. Signals are things that change. They're typically voltages in a radio, but they could be other things. But they're called signals. They're things that change with time. So if I want to process one of those signals so that I can get your voice out of something that I received from my antenna, I could do that with a radio that looks like a piece of equipment with stuff inside, or I could do it with a computer that figures out the signal with software. It's actually nothing but a computer program running in a computer. I can make a radio out of that. That's what a software-defined radio is. So one of the questions is signal processing is performed by software. Now, a signal like a voltage is really in a software-defined radio is not a continuous thing. It's actually points at certain periods of time. So a signal like a voltage is sampled. That is, I say, okay, right now at 2:05, the signal is 5 volts. And then I wait a millionth of a second. So whatever 1/1,000,000th of a second is after 2 o'clock or 2:05, I get the voltage again. That may be like 5 volts. So at 2 o'clock, it's 5 volts. A millionth of a second later, it's it's 5 volts. So a software-defined radio processes these radio signals millions of times a second. So it's really fast, but the actual thing it's doing is really simple. It just does it many, many, many times a second. Now, people like to think of an SDR as something that operates by software. Well, there's a lot of hardware inside of an SDR radio. I mean, you have to do the sampling stuff. That's all electronic hardware. You have to display the result. You have to put stuff out into a speaker so you can hear it. There needs a power supply inside so that you can power this computer. So I find it objectionable to think of an SDR as a piece of software. It's really a computer with all kinds of hardware, but in reality, the actual sequence of stuff that it does to the radio signals, it's done in software. So that's what an SDR is. It's a computer that runs a radio. Now, there's a magic thing called I and Q. I wrote a presentation called What I and Q Can Do For You, but I is nothing more than a vector that's pointing this way. And then Q is another vector that's pointing up 90 degrees from that vector. So there's even a question on that. That's G7, sorry. I lost the page. Sorry, give me a second.
Just back one.
I lost it. Should be here. Yeah. No. Yeah, here. Yeah, this is supposed to be G7. CO9 question. The question says, what's the difference between I and Q? And they're 90 degrees of phase apart. That's a real magic thing to have in a radio, because if I take and I want to send, I don't want to describe this to you. If I want to encode my sound or my data onto this radio signal, there's this really cool thing I can do. I can take, like Pat and Nolan want to send 2 different messages to the other side. I can take Pat's message and I can encode it on the I signal, and I can take Nolan's message and encode it on the Q signal. And when it gets to the other side, I can use I and Q to separate them out again. So the idea of I and Q is that they're like 2 separate channels on a radio, but they mix together such that they're only really using up one little frequency band. And then at the other end, I can separate them if they've been encoded on I and Q. So that's the beauty of having a radio that can operate with I and Q, because it's like two radios, right? And so I can create any kind of modulation with this magic IQ thing. FM, AM, SSB, RTTY, QPSK, all these magic modulation names, they can all be done in the computer with a separate program. So I make a computer program that manages I and Q just right, and I get any kind of modulation I want out of that. That's a pretty cool thing, and I don't have time to do it all for you, but as an example, if maybe it's worth taking a second to talk about that when we're talking about IQ. Suppose Nolan wants to send her voice on the I channel. What I do is I just move the I and the I value back and forth based on how much sound Nolan's making. And then if Pat wants to put hers on the Q signal, then I move the Q signal up and down based on Pat's voice. So I got this going on right now, right? Inside my radio. I got one Q channel and one I channel. And what I do in the radio is I just add them together. It's really cool. I just add them. Like whatever Pat's signal's doing, whatever Nolan's, I physically add them together. So if it was 2 volts and 3 volts, I add them together. When I get to the other end, I can separate them. So I can look at the variation on Q and the variation on I, and I can find out what Pat's saying and what Nolan's saying. That's called amplitude modulation, or AM, like your regular radio. Only it's like 2 AM channels. Each individual one is amplitude modulation. Now, I got this vector, right? I mean, I got this IQ thing, right? I can not only make them go up and down, I can take that vector and I can rotate it around. Well, if I do that and I make the vector go this way, that's frequency modulation. So if I leave the I and Q to be always the same radius, like a circle, and I rotate the circle, that's frequency modulation. And if I make it go this way or that way, I can detect what the other end is doing. So the cool thing about IQ is I can make FM and AM and all kinds, and I can combine them. I can take and I can rotate them and change the magnitudes together. So it's a really cool system, and it's how almost all modern radios work now. So almost all the radios at some point actually have software-defined radio in them, even if they look like they're a big piece of hardware. Okay, so I don't want to beat that to death, but there are 3 questions. What's an SDR? What's the value of I and Q? And that is all types of modulation. And what's the difference in phase between I and Q? And they're separated by 90 degrees. That's all the questions. If you think this isn't good enough, take this link and you will know more about SDR than you ever wanted to know. So it's a very, very common and popular thing now. And it's why it's in the test. SDRs are all over the place. Okay, so what we're going to try to cover the rest of tonight is 2 sections, G4, A, B, C, D, and E, and the modulations, which we've talked a lot about, by the way, in G8, A, B, and C. That's kind of why I got these things connected together, because the topics actually ask different questions, but they're all about the same thing in the seminar weeks that I put together. All right, so let's head into G4, A through E. Okay, G4 is about operating a station. Things about how do you what do you touch on your radio? What does your parts of your radio do? And different things you might do in your shack. So here we are with filters again. How do I get rid of interference in my station? Guess what I could use? A filter. If I have interference that's at a different frequency than the one that I'm using, I can use a filter to chop that stuff out or to reject that noise stuff. So that's one of the things you would do with a filter, is you would do interference rejection by notching away the stuff where the interference actually is. So that's what, I didn't put the question number, but that's what that one's about. I forgot what this question was, but I think it has to do with how do I if I'm using sideband radio for doing Morse code, which is CW, I could use an opposite sideband as a way to reduce interference. Let's see what that question says. That must be G4A. Let's take a quick look at that. I forgot what the actual question was. Okay, it says, what's the purpose of a notch filter? That was the first one. It's to reduce interference. Okay, so the second question in G4 is, what is one advantage of selecting the opposite or reverse sideband when receiving CW signals on a receiver? Oh, okay. If I had a receiver, if I have a thing and the receiver has a little knob on it that says upper sideband, lower sideband, and I'm listening to a Morse code station, and I've got some interference, which is answer C, it may be possible to reduce interference. But the question is, if I change from lower to upper sideband or reverse which one I'm using on my receiver, I might actually get rid of some of that interference. That's what question 2 is about. I should have put the questions in. The third one is split mode. What is normally meant by split mode? Well, this is pretty easy. This is like we do on a repeater. Split mode is when I transmit like at 144.850 and I receive at 145.450 on a repeater. That's what split mode is. I just use different separate. That's the opposite of simplex. Split mode is like not simplex. Wow.
And simplex is you send and receive on the same.
Say again?
Simplex you send and receive on the same.
On the same frequency, right. Split mode, you separate. This next question is like so old, I'm not sure I want to talk about it. What's the reading of the plate current meter of a vacuum tube RF power amplifier? Or saying, what reading do I use on an old radio? I got one in the back down the floor. There were these big tubes inside of power amplifiers, and they measured the amount of current going through the tube. It's called plate current. So they usually have a meter that measures the plate current. And so what you used to do was to find out if you were correctly adjusted. That is, you wanted to see all of the energy go to the antenna. You would tune the radio until that plate current meter dipped. So you saw the meter at reading something like 200 volts or something, and then you'd tune the radio, you'd tune the matching network, and you'd see the meter just dip down. I'm hoping you don't ever have to use that thing because tubes are going away, but that's okay. Tubes are still around, they still get used, and you use a plate current dip to figure out if you're adjusted correctly. And the other one is on automatic level control, ALC. This one's pretty important. If any single sideband, you don't have this on your FM radios, but on your AM, on a single sideband HF radio, which you'll be using as a general, there's an adjustment called the automatic level control. So what it does is it listens to your voice, and it puts it adjusts the amount of transmit power based on the sound of your voice. that adjustment can be changed effectively. If I amplify my voice too much, then I can, if I set my voice amplifier too high, the automatic level control will move the transmitter into too much power. So you can think of automatic level control as an adjustment on your microphone. It's like a send volume adjustment. And you have to set it so that there's usually a meter on the radio. And so you look at a manual and it says, in order to set the ALC, push the button to look at the meter and then adjust this knob called ALC until when you're talking in a microphone, the meter is just sort of in the middle. You don't want it too high, you don't want it too low. If you put it too low, you won't send as much power. So you want to put it high enough so that you send enough power. But if you put it too high, then the amplifier can't follow it and it distorts it and it creates distortion. So it used to be called mic gain, like microphone gain, but on a modern single sideband radio, there's a separate circuit called the automatic level control, and it has an adjustment, and you set it to the middle, and that's what that does is it stops excessive RF. This is not one of the most obvious things on a radio, by the way. When Nancy was getting on when she was first starting out, setting up her HF radio to go on the Wednesday night net, we couldn't hear her. She was like the lowest signal on the net, and we had to really struggle. And I thought it was just going over the hill. Well, it works out she had her ALC adjustment so low that she wasn't putting on any power. So she set her ALC to the right setting, and now she's almost the strongest signal on the whole net. So that's kind of what's going on with that. Okay. Another question is how, these are all separate question kind of things in G4A. How do you match the impedances? Well, you don't have to know about impedances, but the way you match them is you use a tuner. A tuner matches impedance. I almost got to know that. You don't need to know how a tuner works. You just need to know that a tuner is used to match impedance. Let's see, what was this one? An RF amplifier can be damaged if too much power is used. If you drive the thing too hard, it'll burn up. It's just power. Okay. Why was that? This is back to the tube radios. I'm gonna bet you that this question is gone in the next list of the next set of questions. I haven't looked in, but it says what type of device is used to match? That was the tuner. What condition can lead to permanent damage of a solid state amplifier? And the answer is shorting the input signal to ground.
Huh? What?
That was actually a trick. Why is that? Let me look at that one a little bit more carefully. The possible answers are insufficient drive power. Well, if you don't have enough power, you're not going to damage it. Low input SWR. Actually, low input SWR is a good thing. So that's not going to cause damage. Shorting the input signal to ground is not going to put anything out. These are two separate things. Shorting the input is a trick. It sounds like what happens is you're making a short circuit and that's a bad thing. It's not a bad thing in this case. Shorting the input produces no input. You're not going to overdrive an amplifier if you don't put any input in. So the only thing left is D there. a D, which is excessive drive power. I'm trying to explain why that's the answer. Okay. What is the correct alignment for the load or coupling control of a vacuum tube RF amplifier? Correct adjustment. Well, you can look at that. It's answer D is maximum power output without exceeding maximum allowable plate current. Basically, that answer says, I want the most out and I don't want to break it. And that's the answer, okay? The others don't make sense in that. That answer D is the one that makes the most sense. Okay, and C, time delay. Why is there a time delay sometimes included in a transmitter keying circuit? This one's not too obvious, but the whole idea is that a lot of this has to do with a transceiver or a transmitter and a receiver working together. So I'm talking to my radio and I'm transmitting power into the antenna, okay? I now want to go and I want to receive. So I take my finger off the push the talk button. And all of a sudden my receiver is now connected to my antenna. And if there's a built up magnetic field and electric field in the antenna, I could damage my receiver. So there's usually a small period of time before connecting the receiver to the antenna to allow for any of that spurious crap to go away before the receiver is connected. And the way to do that is just put a little time delay in the circuit inside. So when you unkey it, the receiver doesn't get connected till a little bit later. Okay, that's what that's about. Okay. I mean, all these items, there's material about every one of these things that you could talk about, like how big a time delay, how much power does it take, all these things, but they're not in the test. And
yeah, don't confuse us.
Yeah, okay, I'm sorry, but so I'm all right. So let's go continue on. Another word. What's an electronic key? Well, you know what? Everybody got some sense of what a Morse code key looks like, right? And you just push the button. An automatic keyer is just one that you push it on one side and it creates and you push it the other side, it goes da 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 da. So if you go back and forth, you go did it da da did it da da did. But that's an automatic keyer. Okay, it just creates dits and das automatically. On a radio, there's a thing called the intermediate frequency shift control. The word the abbreviation IF means intermediate frequency, not if.
Okay.
Inside almost every modern radio is an intermediate circuit called the intermediate frequency. It's the circuit that's between the actual radio frequency and the actual thing that you listen to, which is the sound if you listen to voice. That's the intermediate frequency, IF. Now, there's a little tuning button called the IF shift on a lot of radios. Sometimes it's called receiver incremental tuning. And you turn it, and it basically just moves the radio tuning a little bit. So that's just a way of getting rid of interference. If somebody's very near your signal and you move the IF shift control a little bit, you can tune the radio and get away from the interference. So that's what that's about. Okay, a dual VFO. Did they tell you what a VFO is? They just tell you a VFO. Let me see, that's in G4. I think they just tell you they just use the word VFO. A VFO is a variable frequency oscillator. It's basically what happens when you just turn the knob on your radio. So when you turn the tuning knob on your radio, you vary the frequency of an internal thing called a variable frequency oscillator. If you've got one of those, you can only listen to one frequency. If you've got two of them in a radio, it's like having two radios. So you can listen to two people at the same time. And I spell frequencies wrong. Yeah.
Frequency.
Okay,
Oh.
so a dual VFO monitors 2. I don't think that's too confusing. And then there's another button called an attenuator. And guess what it does? It attenuates. And so if you've got too much signal going into your receiver, you hit the attenuator button and it will reduce the amount going in and it won't overload it. A lot of times, if you get a very loud signal, you turning the knob down to not hear it isn't helping, because you really want the signal level to be smaller so that it doesn't get distorted. So a lot of receivers have a thing called an attenuator to reduce overload from a received signal. It's too loud. And here's our ALC again. That's in another question. That's some of these questions, by the way, use the same word like 4 or 5 questions apart. It's actually the same topic. They just want to throw in another question about the same topic to fool you or to select from in the test. Because they want you to know what an ALC is. Whether they ask you question A or B, they still want you to know it's an ALC, what an ALC is. So an automatic level control, if it's not adjusted right, will put too much energy into the transmitter, make it too loud and cause distortion. There's an answer that has to do with AFSK that has nothing to do with the question. It's just in there to distract you with another crazy word called AFSK, which we'll talk about in a little bit later. Okay, any questions on that stuff?
I don't really understand.
Yeah, Nolan, you got to get closer to the mic when you talk. You.
Okay, where is the mic?
I have no idea.
I mean, Pat's right on the mic and Nolan's off to the side, and I keep missing you. Go ahead.
I didn't really understand what the question was at ALC, not adjusted by mic gain properly.
Okay. A lot of times, the way you adjust the ALC is to adjust the mic gain control. Some radios actually have a button that says ALC or a tuning knob. Others, usually, there's a knob that says microphone gain, how much sound. So if the ALC is the circuit that tries to adjust the sound to the right level, if you put too much sound into it, it drives it too high. It can't compensate for it and it'll create distortion. If you put it too low, then you're not transmitting all the power you can. So
it might be a microphone gain button.
Yeah, a knob, yeah.
No.
It might be an up-down button too. You know, it could be on some of the digital radios, there's actually a button. You press it up, it makes it go louder. You push it down, it makes it go softer. At one time, it was always a little knob.
Okay.
Okay. All right.
Thank you.
All right, no problem. Okay. Let's see. I think the question is, what's the question? G4. I lost the question here. G4. Oh yeah. Which of the following can be a symptom of transmitted RF being picked up by an audio cable carrying AFSK data signals between a computer and a transceiver? This is a mouthful for you. Okay, they threw all kinds of words at you in here. So basically what this is I've got a keyboard kind of thing, and it's sending data over to my radio. And one of the modes I might do that in is called audio frequency shift keying. So that's like a distraction. But basically, I've got a computer next to my radio, and my microphone is picking up signals that I don't see. Like I don't hear them because they're above my hearing range. So they want to know, if you hear something picking up in your microphone, what could cause that? Okay, and so first, this question has so many words in it, it's crazy. What's VOX? VOX is voice operated relay. That's a system where you don't have to do the push to talk button. You push the talk button, turns on your transmitter. There's also a circuit that listens to see how much sound you're making. And if you make enough sound, it'll turn on the transmitter automatically. So you don't have to push it. So when you're talking to radio, it effectively pushes the push the talk button for you. Well, that's not great if there's a dog barking in the background. Okay. You know, so, or something going on in the background. So if your transmitter is setting off, you may have your voice operated relay turned on, and that's one way you might pick up some audio. It's actually about radio frequency stuff getting picked up by your microphone. So the answer to this one is everything's bad. So the answer is all of them. If you have distortion, that could cause it. The frequency connection timeouts, that's another distractor of significant. But in this case, all of those things can cause distortion, accidental switching, changing the frequency of your, you might get the effect that some frequencies are not at others. That's a real tricky one in there, but the answer is all of them, okay?
Okay, thank you.
All right, let's see, 15, 16. Noise blanker, I don't know that I said anything about noise blanker, did I? How does a noise blanker work?
It blanks noises.
Well, if the noise blankers don't work all that good anymore, but anyway, a noise like a lightning bolt down, you know, in Connecticut goes off, and it makes a static crash in your receiver. Okay, one way to make the receiver make that go away is to look for something that bursts very quickly, because voice doesn't do that. When you're talking, voice doesn't change that instantaneously. So a noise blanker circuit says if anything changes really fast by a lot, I'm going to just shut the receiver off for a very small period of time. And that's what a noise blanker does. It blanks out noise signals, okay? So it changes the amount of gain allowed. That is, it basically just shuts it off. It doesn't like completely shut it off. It just makes it softer for a very short period of time. Let's see. On this page, the word audio frequency shift keying is used all over the place to confuse you. This is very simple thing, audio frequency shift keying. Basically, if I have a radio that can send voice or audio from A to B, like an FM radio or a single sideband radio, I can encode data in the voice. For instance, I could say, I could whistle. I could go when I'm talking on my voice audio channel, and you could determine that I was going high, low, high, low, high, low, right? By just listening to the sound. Well, what I'm doing is I'm taking my sound frequency, which is a whistle or a tone that I'm playing on a piano. I could do this with a piano. Piano would be a good example. I play middle C on the piano, and you hear that, and then I switch to E, and then I go back and forth between C and E, C and E. You would be able to detect that. So I'm I'm frequency shift keying. I'm changing my frequency, but I'm doing it by just sending you audio. That's what audio frequency shift keying is. Basically, you just have a voice channel and you did different tones inside the voice channel in order to send information. If you ever use an old computer modem? Anybody use an old computer modem, like to do a connection to AOL? You dial on with a modem.
Oh, yeah. Oh, yes.
Yeah.
And then you transmit your data, and then you could type on the internet.
Yes.
Well, the telephone is an audio channel, just like your radio is. And the modem, what it would do is it would send these tones on the telephone. That's audio frequency shift keying.
Oh,
So AFSK is making different frequency sounds on a voice channel. and it's called a modulation type. It sends digital data because usually, think of the AOL thing. Maybe the AOL connected with audio frequency shift keying makes sense. You know, to some people who know about AOL. Some people don't know about AOL, but
I still use AOL?
I had
well, yeah,
nothing.
AOL. I mean AOL when the old days of calling it with a modem
Dial-up.
instead of the internet.
It was dial-up, right?
Yeah. Okay, so let's see. Whoops. Okay, so what's the difference between this audio frequency shift keying and just frequency shift keying? Well, not a whole lot, as it works out. But in audio frequency shift keying, you're just sending a tone on an audio channel. In frequency shift keying, you're actually taking the transmitter and you're moving it back and forth between one frequency and another. Follow that? So if I have an FM does that with your voice. Your voice changes the frequency depending on what you're saying on your voice. So if you don't do it on an audio channel, it's frequency shift keying. If you do it as part of an audio channel, it's called audio frequency shift keying.
Oh, okay.
It has nothing to do with the test. But theoretically, they're the same thing. If I change frequencies on an audio channel, I'm doing the same thing as I'm doing with frequency shift keying. It's just that I have a thing called an audio channel and then I use it. And if I don't have that audio thing and I just shift the frequency, then I don't call it audio frequency shift keying. I just call it vanilla frequency shift keying. Okay. So a lot of use of this audio frequency shift keying thing in the exam. It drives me crazy. It's really almost a silly topic, but that's okay. I'm gonna skip that section there. All right, so let's see. I gotta move on with B here. So in section B of G4, the highlighted words here are the things that exist on the exam, okay? That's part of what I did on the slides. If a thing is bolded on this slide, the word exists on the test. So there's 3 questions about oscilloscopes. You know what an oscilloscope is? Ever seen one? Didn't think of showing you one. I got a few of them over here.
EKG
Pull one out just for fun. Hold on a second. Give me a second.
shows the
Radio frequency.
I should have had one out. This is classically what people think of as an oscilloscope. Piece of test equipment, got a handle on it. It's got a screen and a bunch of knobs. Okay. What this does is it lets you look at the variation in an electrical voltage. So if the voltage is going up and down, you can see the oscilloscope beam move up and down. And if it's moving up and down in time, and I stretch and I move the beam this way at the same time that it's going up and down, I can actually see the shape. Okay, so think of maybe take a rod like a that you get in the garden, and you shake the rod like this. You'll only see the thing going up and down. But if I move the rod across as I'm shaking it, and you watch the tip of the rod, you'd actually see the time-dependent position of the rod. You see that?
Oh, yes.
So that's what an oscilloscope does. So
allows you to look at variation in what?
time and voltage.
Time and voltage. Okay.
It's an extremely handy instrument. To me, it's like a wrench to do it. I mean, it'd be like a car mechanic without a wrench. It's just the most versatile tool around. So there's 3 questions on oscilloscopes: G4, GB, I guess, B, B1, B1. What's the advantage of an oscilloscope versus a voltmeter? Well, you can look at complex things, waveforms that change. Voltmeter just goes like, like it reads 5 volts and then a little bit later reads 3 volts. There's nothing to tell you how it's changing in between. The other one is, which of the following is an advantage of an oscilloscope versus a voltmeter? Oh, the first question is, what has horizontal and vertical channels? Deflection. That's an oscilloscope. We just talked about looking at time and voltage. On question 2, you can look at complex waveforms. It's not an impedance meter, it's a voltmeter. It's just a voltmeter that can look at time as well. And which of the following is the best instrument to use when checking a waveform? Oscilloscopes just about beat everything when it comes to looking at time. So that's those 3 questions. It's 3 of those. Whoops, I'm on the wrong slide. Sorry about that. Okay, a voltmeter says, why do you want a high impedance voltmeter? I think is the question. Why is high impedance desirable for a voltmeter? Well, if you have a high impedance, you don't draw any current if you touch something with it. Get a voltmeter. Here's a voltmeter. It's called a multimeter, actually. All right, you've probably seen these around. 2 leads. What? I'll turn it on, but you won't see it. It's got a little digital meter on it, right? Well, if you go and stick this stick this in a circuit, and it's a short circuit, that's not going to be good for the circuit. It's like sticking a screwdriver in an electrical socket. Not a good thing. But if you put a light bulb in a socket, which has a higher impedance than a short circuit, it works fine. So think of it as like plugging something into a socket that just doesn't draw any current, and therefore it doesn't affect anything. So the higher the impedance, that's better because it doesn't change what you're measuring. And I get another spelling error in here, right? Looks like I got more slides to change. All right. The other, I don't know, what's the other one is, what's the advantage of a digital voltmeter? I didn't put that one. Well, actually the word, well, the answer is digital typically has more precision than analog. So if I want to try to read a scale, if I want to read a scale, and it's like 2.3, I'm going to have trouble seeing 2.323. If I've got a meter, it might be able to read to that accuracy. So that's what's going on with that one. Now, field strength meter. Let's see, what was that one? Oh, a 2-tone test. All right. Oh, geez, another spelling error. Wow. Well, you guys are helping me fix all these errors.
Well, while you're at it, go back to typically and take the the extra eye out.
Yeah.
Typically, you put in a good eye, but
It takes it out.
You didn't take the old eye out. Digital, it's the sentence.
Oh, wait a minute. It's not. No, it's HAR, harmonic. Well,
Yeah.
What happens is if I just put in one signal, I don't necessarily test my whole system out. And if I put in two tones like C and E, which are harmonically related, that's not as good. So what you typically do is you like use C and F sharp, something like that. You guys music fans? I don't know.
Yeah.
So a non-harmonic tone is something that's dissonant, like something that's not in the same scale. So, and if you use that, the other end, it's a good way of checking to find out if what comes in is the same as what goes out. And that's called linearity. In other words, if I put two things in and they come out independently, that's good. If they mix together and somehow distort, that's bad. So there's this thing called a two-tone test to find that out. Okay, a field strength meter is basically a probe you put in the air, and it tells you how much radio signal is coming off your antenna. Simple enough, right? I got one of those now that I think of it.
Of course you do. What does it measure?
This is a very crude one. It had a little antenna on the top. This was just a very crude field strength meter that I had when I was a kid. Basically, if you get near the antenna, the meter goes up, and if you move away from the antenna, the meter goes down. That's a field strength meter. Okay. Well, let's suppose that the antenna transmits exactly the same in all directions. I could take my field strength meter at 5 feet away and just go around the antenna in a circle, and it would show me that it was the same everywhere.
Sure.
Right? Well, the other thing I can do is if I have a directional antenna, then I can point this at the antenna and I should see a lot of signal. And then if I move it over here, I'm going to see less. And if I put it back, it comes back. If I put it over here, I see more. So if I wanted to see the directional capability of my antenna, I could just take a field strength meter and move it around like that. Go all the way around. I could do it fancy, but that's basically what they're talking about. Okay.
Thank you.
Okay. So let's see. Directional. A directional watt meter. It's a little tricky. I got one of those too. I didn't know I had all. I didn't realize I had all these things sitting around. This is a watt meter. Guess what it measures? Watts.
Oh, very good.
Okay, so if I put it in, I can measure power with it. But the cool thing about it is it's got a button on it that says forward and reverse. Now, remember, or if you don't remember, we talk about these standing wave ratio things all the time, SWRs. Basically, what it means is if I put a wave towards my antenna, like if I was shining a light at a mirror, okay? If I shine a light at a mirror, what happens?
It shines back at you.
Shines back at me. So there's power going this way, and there's power going that way. I put a piece of glass over here, and I send my light beam this way, nothing comes back. Okay. If I put something in between, some of it comes back, some of it stays over there. Radio waves do exactly the same thing because they're the same thing. Light and radio waves, same thing. The ideal thing, though, for an antenna is that if I send a wave this way, I would like all of that wave to go out my antenna and go to the world. I don't want any of it coming back because any of it coming back got wasted. Okay. So the ideal thing is for all the power I send to stay there and go away, heat up the glass, whatever it does. If I have, in order to find out how much is going one way and how much is going the other way, I can use a magic thing called a directional wattmeter. And when I put it in the forward direction, it tells me how much energy is going out to the antenna. And if I put it in the reverse direction, it tells me how much energy is going in the other direction. So it's a directional wattmeter. There's a million of these things, but this is one that came off a CB radio, as sacrilegious as that sounds. And the ratio of how much is going one way to the other way is the standing wave ratio. And that's what SWR is all about. So you use these meters to measure standing wave ratio. That's why I use a directional wattmeter, because SWR is the ratio of forward to reverse. And if you don't know the power in each direction, you're not going to get the SWR. Wonder what other good stuff I got over here. Okay. All right. The next thing is an antenna analyzer. My favorite thing. I call it a VNA. I like to think of it as, I have one. I do have one of those too. This is the one we bought for the Aten project, the microwave project. This is a nice one. So I call it a very nice analyzer instead of a vector network analyzer. Right. And this was one where you can actually see the guts of it.
Wow.
And you see those little, these guys over here? Not the green thing in the middle, but all the little things in the middle. Those are all called directional couplers. What they do is they extract the energy going, some of them extract the energy going this way, and some extract the energy going that way. And one's in forward and one's in reverse. And they measure the amount of forward and reflected energy, same as this thing. Okay, it's just measuring forward and reflected energy. But the cool thing about a VNA is it just doesn't tell you the power, it tells you the vector shape of the energy. So you not only know you don't only know the magnitude, but you know the phase. So that's a VNA. And you use a VNA typically to span a bunch of frequencies and get the impedance of an antenna. So it's really the tool that you use to measure impedance of a device like an antenna or a filter. You can use it to measure a filter. You can use it to measure all kinds of stuff where you want to know power and phase. So that's an antenna analyzer. I like to call mine a very nice analyzer, VNA. So it measures impedance of a coaxial line and anything else, actually. It's really a fancy version of this that works at radio frequencies. So I don't want to scare anybody with VNAs, so I call them very nice analyzers. And then the other question is an analog instrument. An analog instrument is something like this, which has a meter on it, little meter, versus a digital instrument, which has a digital number on it. If I want to tune something, like I want to make it the maximum or I want to make it the minimum, it's much easier to use one that's got the little, it's a meter like this, an analog meter. That way I can see that I got right to the end. You know, I'm trying to get it to the peak, or I'm trying to get it to the minimum. If I have a bunch of numbers, I don't know. Like if it's reading 2.3 and then it goes to 2.12, is that bigger or smaller or what? So a digital instrument isn't as good for tuning as a meter. They're all meters in the sense that they measure something, but an analog meter has a needle in it that tells you where it's at. Okay, the digital instrument just gives you a number, and that's more accurate. So there's two questions: one for digital meters, one for analog meters. and so forth. Okay, section C of G4, getting behind again. Grounding and digital signal process. Let me say this one, G4, C. Let me just grab an example question just so I'm getting tuned in here. G4C, which of the following might be useful in reducing RF interference in audio frequency devices? Well, the answer is the capacitor, because a capacitor will short radio frequency, high frequencies to ground. So it's basically looking like a short circuit to the interference. It's driving the interference to ground. That's a pretty complicated subject, actually. And however, it's a very typical problem. If you have interference, you might put a capacitor in and short it, and it'll reduce the noise to ground. It's like a filter, actually, if you think of it. It's actually a filter, but it's a very specific question in this case.
Capacitors.
Let's see, C2. Which of the following could be a cause of interference covering a wide range of frequencies? Arcing is the answer. Arcing is the answer. Think of it as a lightning bolt. So a lightning bolt will create noise everywhere. And arcing is the same thing as a lightning bolt, only a small one. So it's a tiny, tiny lightning bolt. Let's see. Another question is, your single sideband radio is causing interference to a telephone. Every time you turn on the radio, somebody hears crackling or something on the telephone. And what's the question? What sound is heard from an audio device or telephone if there's an interference from a single sideband? So, well, if I'm just turning my radio on and somebody hears something on the phone, they're not going to hear humming, and nothing related to humming going on. Anything steady is not going to go on because, so they use the word humming in here a lot to distract you. No humming. And typically the signal's not going to come through. The thing that's hearing the noise, it's really just picking up parts of it. So it's going to be distorted. The answer, clearly audible speech, you throw that one out because you usually don't get an exact clean signal when it's noise like that, but you don't hear humming either. So you might hear speech, but it'll be distorted. I don't know if that helps clarify it for you, but that's what's going on. Which is the effect of an audio device when there's interference from a Morse code thing? Well, no more humming. Well, there is humming in that case, but clicking is the key element. If somebody's sending Morse code, da 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 da, you're not going to hear distorted speech. You're going to hear clicking. So clicking is the best indicator to what the right answer is there. You're not going to hear audio because it's CW. So they stuck humming in there. I don't know why.
But CW still makes a noise.
Yes, but it's
so why isn't that audio?
Well, they use the word. Wait a minute. What is it? What is the effect? Well, they use the term nearly pure audio frequency, which would not be the case because It's not just a continuous sound because it's going on and off. You know what I'm saying? You know, it's they're using words in here to try to trick you, like, but they claim nearly pure audio frequencies. So that's you're not going to hear one tone. You're going to hear sound, but you're not going to hear tone. You're not actually going to hear the CW either. You're going to hear, so chirpy Morse code is got Morse code in it. That's wrong. And you're not going to hear the sound like severely distorted audio. You're going to hear clicking. So I don't know. I wouldn't have written it this way, but clicking is the only magic thing that is probably most correct in this case. So the answer is clicking. Okay, RF burn. I put these notes in here to remind me of what's going on, but I should have clarified the answers. You should get an RF. Let's see, what was the question? What might be the problem if you receive an RF burn when touching your equipment when it's transmitting? Well, it's not normally, you're not going to get an RF burn if you're not transmitting. What are they're trying to tell you? Okay, the concept here is I put a ground line in my antenna system. I got a good ground. I think I've got a good ground. So if I had a lightning bolt goes to ground. Lovely. But a solid ground could have chemical distortion on it or a little separation and so forth. So the ground might be a ground to low frequencies, but it doesn't have to be a ground to high frequencies. It might be, but what they're trying to make you understand here is that just because it looks like a ground at one frequency doesn't mean it's a ground at another frequency. And usually the higher the frequency, the more difference it becomes to the ground. So if you get a burn, it's because the RF energy is not being protected. You're not being protected from the RF energy because there's a high impedance at the high frequencies in the radio frequency range. So what they're really trying to do is not give you an RF burn, because RF burns are dangerous, by the way. They will create third-degree burns. You know, you'll appreciate this, Nolan. You know, an RF burn tends to be below the skin, so you can get really bad burns and not have them show up as smoke coming off your hand. Okay. So RF burns can be dangerous, but you can get a mild RF burn and it's okay. But if you were to, be moving around near your antenna wires and stuff, and all of a sudden you felt some tingling in RF, and you say, well, it can't be that because I've got a good ground. That's not necessarily the case. And that's what they're trying to make you aware of. And this is an awareness question. This is one of the things that you should look for that you might not look for otherwise. That's why they're telling you about that. Let's see. Yeah, the first rule is don't get an RF burn.
Exactly.
Because they're not good, okay? Let's see, which of the following would reduce RF interference? No, that's not a burn throw. What was the question? You get burned. There's several questions in here about burns.
I should get those right.
Yeah, this has to do with if you have poor grounds, you have poor grounds and grounds that are not necessarily, the grounds can be different at different frequencies. That's the point. And so you might think you've got a ground someplace, but it's not necessarily an RF ground. And if one way to detect that, if you detect that you're getting RF kind of burns, you should start looking around at the grounds and making sure that they're not high impedance at RF frequencies. And when you get RF burns, I would suggest you ask somebody to help you find the problem and not just sit there and get burnt. And that's a practical solution here. Again, this ground rod thing could be a really good ground for lightning, but not necessarily good ground at 6 meters or something. So just keep when you're trying to answer these questions, keep in mind that a ground and radio frequency may not be equal to a ground at low frequencies, and that's what they're trying to make you understand.
Okay, got it.
Let's see. This could get back to you. That's not you again. That's your station equipment, I think. I think I get a little too fast. This could get back. I'm just trying to find the question that relates to this. This is G4C, right? Yeah. How do they mix? What could be a symptom of a ground loop somewhere in your system? And you receive a hum versus SWR has nothing to do with that. Too much current has nothing to do with ground loops. And somebody gives you a harmonic interference report, which is just off the wall. So a ground loop tends to produce hum, and that's the typical learning there. Okay. If you have a ground connection that's been soldered with lead or something, and a lightning strike hit it, there could be enough heat that the solder would melt. So after the lightning strike, you may not have the connection you thought you had when you first soldered it. So they're trying to make you aware of the fact that even a small lightning strike might actually open up a solder joint. And a common mode current is a
the current reduction.
Yeah, well,
this
is a case where you've determined somehow by magic that you have a common mode current. Okay, I mean, how did you do that? I don't know. I'm looking around my shack. Oh, I got common mode currents. There they are. Like that. So I want to get rid of them. Well, one way to get rid of them is to put a ferrite or a piece of make a coil, or take one of these chokes, and you put it around the cable. You've all seen these on cables. They're little round cylindrical things that are on most computer cables these days. Those are ferrite chokes. They're just iron type of material, and they will stop current from going through them if the current is in the same direction. So here's what happens. I got this coaxial cable, this piece of wire, and there's currents going on the shield and there's currents going in the middle.
Yeah.
I could have two wires, and I got current going this way and current going this way.
Yeah.
If the two currents are opposing each other, there's no radiation coming off of that. They cancel. If they're going in the same direction, they add. So the field from this one and the field from this one adds. So when the currents are flowing in the same direction, that's called a common mode current. And that's not good, because that means something's not balanced in the system. If I have a light bulb and I feed power to the light bulb, all of the current going to the light bulb should come back in the other direction, right? Follow that? If I had a light bulb and
Yes.
I measured the current on one of the black wires, say, to go into the light bulb, I should measure exactly the same thing on a white wire coming back.
Got it.
Okay? If I don't, there's some current that's common to both leads. It's not opposite. That's what a common mode current is. Now, there's an interesting safety thing I can throw in here. You know what a ground fault interrupter is on your you've had
Yes.
ground fault interrupters in your house? You know how they work?
Yes.
They look for that difference current. If the current going this way is not equal to the current going that way, that's a fault. That current, the stuff that's left over went someplace. And that someplace is usually a fault to ground or a person grabbing onto the line. So that's why ground fault interrupters work. They measure the amount of current going in opposite directions, expect to see exactly the same thing. And when they don't see exactly the same thing, they trip and shut the circuit off. So that's sort of the opposite of common mode current. Okay, if everything's working normally, the currents are in opposite directions. If you have a fault, some of the current will be flowing equally on both sides. They won't be balanced. And the unbalanced, you can cancel with a ferrite. Okay? I don't know. I hope that helps.
Yes, thank you.
Okay, in section D is speech processes. Speech processes are a magic black box again. You put some speech in, like with noise from your radio receiver. Okay, so you got a signal coming off your receiver and it's got some noise in it. And you put it in this black box and out comes no noise, just the sound. It's magic. That's a speech processor. Why would you put one in? Well, if you don't have as much noise, you can more intelligent, you can increase the intelligibility. What was the point of the question here? I'm trying to remember the shoot, I forgot the answer. What's the purpose of a speech processor? Well, it's not to make the sound louder, so it's not to increase the average power. I should have made that, the answer is A. So these guys here should actually be, I don't think these should be, I don't think those should be lit up. The answer is increase intelligibility. A speech processor does not increase the average power. Otherwise, it would be an amplifier. It doesn't automatically oh, wait a minute. This is several questions. Sorry. These are all individual answer questions. Oops. All of these things are correct answers.
Something. Yeah, I just posted them.
Looks like I was going to get this one wrong if I answered it. Why does it increase the average power? This is one of those questions where all the other ones are wrong, and the only one that might be right is the increased average power, because it doesn't do the other things. It doesn't try to increase the peak power. It's trying to create, it's trying to get rid of the noise is what it's trying to do. And so it will get rid of, I don't think I'm doing justice to this question. I can tell you that A, C, and D are wrong, but I don't quite understand why increasing the average power is definitely what a speech processor does. But the others are clearly wrong because it does not try to do distortion or who's calling me now? I just, yeah, Mark, I'm in the middle of class, right? Call you back.
Mark.
Yep. Go ahead. Goodbye. Anyway, okay, so all right, so so these were three different questions. The first answer was increased intelligibility. The second answer is a good thing that they do is increase the average power, not the peak power. And they don't take out other kinds of harmonic distortion. They don't do that. They're really trying to reduce noise. And the incorrect, if you don't have a speech processor adjusted correctly, everything goes bad. So the answer is D. Distortion, splatter, and excessive background pickup all happen. So incorrect adjustment causes many bad things. That's an answer where all of the above are correct. Okay. S meters. S meters are very common on most receivers. They look like this thing at the bottom. They're trying to tell you if the signal is strong or weak. And there's a magic setting at 9. See where it says 9 over here? Mm-hmm. That's called, people call that S9 because it's 9 on the S meter or the signal strength meter. And that relates to a very specific amount of power coming in from the receiver. And the idea behind this is if it's less than 9, the power is less. And if it's more than 9, the power is more. And it measures things in decibels, dBs. And if it's 20 dBs over S9, that is, like it says, plus 20 over here, mm-hmm. That means it's 100 times more. Now, I can calculate why it's 100 times more, and here's the math. It's 10 raised to the 20 divided by 10 power, or 10 squared produces 100. I think if the only questions are, let's see, 20 dB, the answer is more, and it's 100 times more. And then they want to know what the difference between S8 and S9 is. And the answer is 6 dB or 4 times. I think 4 times is the only thing in the test. G4D. Which version? Oh, G4D, sorry. Okay, so it says, how does a signal that reads 20 dB over S9, that's when it's reading up here, you call that plus 20 or 20 dB over S9, compare to one that's in a correctly calibrated meter. It's 100 times. All right. The other one is, where is an S meter found? It's on a receiver because it tells you to receive signal strength. That's not too tricky. And the other one is approximately 4 times or 6 dB. That was a choice, and 6 dB is twice 3 dB. So if 3 dB was 2, 6 dB is 4. And there's the math to support it, but You only need to know those three things about S meters. 4 times per increment. So 5 to 6 or 6 to 7 or 7 to 8, those are all 4 times power. And when you're 20 over, it's 100.
Got it.
That's how these things are calibrated. Any questions on S meters? I think that's pretty straightforward.
And
You
the
gotta
S
remember-
meter is found on the receiver.
And it's always on a receiver. It's just the receive
Okay.
signal level. So that's what an S meter does. What would measure the transmit signal strength?
Antenna.
No, we talked about a directional one.
Oh. Field strength meter?
That's one way. There's another way too.
Oh, directional
Watt meter.
watt meter?
Yeah, a watt meter would measure the amount of signal transmitted. So transmit signal strength is typically measured with a watt meter. If you want to find out how much is going in each direction, you use a directional watt meter. And a field strength meter wouldn't have been a bad choice either. You could determine that your transmitter was putting out more or less, but it wouldn't be a very calibrated one. Whereas a watt meter would be a more accurate instrument.
More accurate.
Okay. Good guess though, Nolan. That's actually a correct answer. Okay. Single sideband.
Transmitter.
That's in D. It's also in D. Okay. I think this is a little tricky subject because single sideband can be a mystical thing if you, in a lot of ways. Just to let you know that if you think you're confused about single sideband, don't feel bad because I was confused about it for years. I mean, I know what it is, but it's actually pretty complex mathematically as to what it does. So I'm going to try to give you some insight. First of all, there's a thing called double sideband instead of single.
Right.
And most AM radio stations are called, use double sideband AM. And you can create that with an unbalanced modulator. That is a modulator that's not balanced. The reason I'm bringing that up is there's another question about a balanced modulator. So to create amplitude modulation, you might use an unbalanced modulator. And it creates an identical copy of your sound above and below the frequency setting of your radio, which we'll call a carrier frequency, because it's the middle frequency of the double sideband. People used to think of it as a carrier because it carried the waves. Well, it works out that that ain't exactly true, but that's okay. Common vernacular is the middle frequency of the AM is the carrier frequency. Well, in this case, you transmit the same thing 2 times, and that's a waste. So if somebody got the idea, hey, suppose I only transmit 1/2 of this thing. Isn't that more, isn't that better? I put it all on one side. I don't have to send it twice. I just send it once. That's what single sideband tries to do. So one way to create single sideband is to create double sideband because it works out that's easy to do. And then you put a filter, remember I made you a filter, and you just take away or reject one side or the other. That's one way to make single sideband. Use a filter that has, you have the signal with 2, like a passband filter, and you throw this one away or you throw this one away. It works out that's pretty hard to do. It's easy in concept, but building a filter with that very fast transition that we talked about is very hard. So that's not the best way to generate single sideband. Now, what was the thing we used to generate any kind of modulation we ever wanted in the software-defined radio? What were those things called?
The speed of.
One's 90 degrees from the other.
Oh, vectors.
Vectors.
What is it?
Vectors, I and the Q.
Vectors, yeah, it's a vector, I and Q. The I and Q vectors can be used to great effect to create single sideband. And I'm going to leave it at that because it's a very complicated subject mathematically. But when I'm transmitting a voice signal on a single sideband, my voice signal is about 3 kilohertz wide, 3,000 hertz wide. Oh, another K.
Another K. Got it.
Single sideband, if it's set properly, should transmit about 3,000 or 0.003 megahertz. Okay.
Got it.
So if your carrier, if your radio is set to 39,000,000 and you use upper sideband, what's the highest frequency that you are transmitting? So I would add 0.003 to my megahertz number. So my megahertz number is 3.9. So what's the highest frequency I transmit if I set my radio at 3.9 and I am using upper sideband?
Wait a minute.
What you think about that?
Yeah.
What I would do is I would add
4.2.
Excuse me, what was that?
4.2 for the upper.
Nope. I'm only adding 0.003. So it's 3.900 and I add 0.003. So it's 3.903. Let you catch up to that.
Right.
Okay.
Right. My mistake.
Yeah. Now, if I use lower sideband and my carrier is 7.178, what's the lowest frequency that I transmit?
Well, the answer is right here.
Well, yeah.
7.175.
That's why I get the big bucks. You know what I mean? All right. So there's another question that's precisely in the exam. Now, why is this important? The reason this is important is if you're in the middle of the band someplace, it really doesn't matter that much because you're just going up or down a little bit. Right. But if you're right near the edge of the band where you're not allowed to operate and you set your transmitter to the end of the band, right, and you're at the high end and you transmit up a sideband, you're transmitting illegally. You're transmitting out of band. So you have to set your receiver below the band edge by 0.003 if you're transmitting upper sideband. And conversely, if you're at the low end of the band and you're using lower sideband, you're going to fall off the end. If you've got the meter set, if you've got your frequency tuner thing set to the very edge of the band. That's what they're trying to tell you in here. So they want you to know that, you know, in double sideband AM, the frequency thing is the middle of that. So in that case, you're transmitting below and above all the time. And so if you're AM, you better stay away from both band edges. Okay. But if you're single sideband, yeah. But if you're single sideband, you got to know if it's upper or lower, because it's going to depend whether you're at the upper end of the band or the lower end of the band.
Right.
And that's what they're trying to tell you. You can play with the math here. I don't think it's that complicated, but the whole idea is don't go past the edge of the band. That's what they're trying to keep you from doing.
Exactly.
Okay. So then they ask you if you're on the low edge and you're in lower singles and you're in lower sideband, set the carrier above the edge of the band. And if you're on the upper edge, set the carrier below the edge of the band by at least 0.003.
Right.
Yes.
What's a carrier?
Oh yeah, the carrier is the frequency that your radio shows on the front. So if you set your radio to 3.900, that's the carrier. Now, why is it the carrier? Well, it represents the position of the radio somewhere in the band. At one time, it was the middle of the AM band. Like if you were on AM and you were at listening to WBZ at 1.03 megahertz, the middle of the band was 1.03. That was called a carrier frequency.
Okay.
Now, it works out that you don't really transmit at the carrier frequency. You transmit above it or below it, or sometimes both sides. The information is all over the place. It's not the one frequency that's carrying the information. It's all the frequencies around that place. But we have to pick some reference, and the reference that people pick, they call it the carrier frequency. And it's the thing that they put on the front of your radio when you turn the knob. So when you turn the knob to 3.900, everybody agrees that that's the carrier frequency to do all your other thinking around. So if you're in upper sideband, you're transmitting above the carrier. If you're in lower sideband, you're transmitting below the carrier. And the carrier word came from the fact that your sound is being carried by the radio wave.
Okay.
Okay, so the term carrier frequency is a little wacko, but the carrying part is true. But if you were to just this is an information theory point. If you only transmitted a carrier, only that frequency, you could not send any information. The only reason you can send information on a radio signal is because you move the signal around near the carrier frequency.
Okay.
You might think, no, that's not true. Paul's like crazy, because if I turn the thing on, I know it's on, right? So I'm sending you some information. I'm telling you the carrier frequency's on, right? Doesn't that sound like information?
Yes.
Well, the only way you know it's on is for me to shut it off. So at some point, it was off and now it's on. Or if it was on, I got to shut it off. So as soon as I change that, I'm adding frequencies to the signal. So turning Morse code on and off is not one frequency. It's a bunch of frequencies around the carrier frequency.
Okay.
And that's a very fundamental radio piece of knowledge. Information requires changes in frequency. Okay. All right. Anyway. All right. So now we're done with that, and it's already 8:30, and I never even got to this. Well, let me try to get through these antenna things. The G4E is on mobile operations and antennas. So I got some pictures here. They have a thing called a capacitance hat. There's a picture of one. It's actually not a hat at all, but it's like a set of radials, if you will, around the top of the antenna. That's a capacitance hat. It's used to create capacitance and therefore shorten the antenna. So that's actually, wait a minute, you know what? Oh yeah, that's question G4E01. Okay. The question is, if you put a capacitance hat, what do you do? And what you do is you electrically lengthen a short antenna. So if the antenna is, you made it too small, or you can't fit it in your house, you can make it look longer by adding a hat. So you can make it look like a long antenna by adding a hat, but not forever. But I mean, if you can't fit the antenna in or your neighbor won't let you put one up that's long enough, you can use a capacitance hat to lengthen it, and not actually lengthen it. It's electrically shorter.
Okay.
Let's see. I think the answer to that one is an electrically. Why did I move this out of the way? Electrically short antenna efficiency is typically low. So if I put an antenna that's too short, my antenna efficiency will be low, and it will also limit the amount of frequencies I can send on the same antenna. That's question E6. So these are all related to electrically short, making an antenna longer. If I want to make it longer, I can put a hat. If it's already too short, my efficiency is going to go down and my bandwidth is going to go down. So it's important to get the antenna the right length, but sometimes you can't do that because of other limitations. There's also a question on E2 about a corona ball. That's a small metal sphere at the tip of there's a picture of one right there. So you see that's what I just want to show you what the picture looks like. There's two things that corona balls do. They can, if you have a very sharp antenna, you can get discharge, like Tesla coil effect kind of thing around the antenna, and that's one way to suppress it. The answer to the battery question is the large conductor. G4E. Yeah, the question E6 was one disadvantage of using a shortened antenna as opposed to a full-size one. And the operating bandwidth can be limited. Okay, so let me go to which of the following may cause receive interference in a radio installed in a vehicle?
The alternator.
Right, which is the alternator, the vehicle control computer, or the fuel delivery system. All those things turn things on and off. And, the answer is all of them.
Okay.
Anything clicking noises and stuff will cause interference.
So like the ignition.
Yeah, the ignition system, or the alternator, all those things. But the question has battery charging, fuel delivery, vehicle computer. The one that's probably not obvious is the fuel delivery system. That's kind of a trick. But the fuel delivery system is turning the fuel on and off, on and off, on and off very fast. And the electrical circuit that does that can cause interference because it's changing the bloody frequency again. Okay. Okay. a lot of us now know what creates sunlight directly into electricity. It's a photovoltaic or PV conversion. That's a solar panel. There's one here on, is it this one? I think it put on the next page. Oh yeah, okay. The questions in the exam poll are out of order from here because they're just like on completely different subjects. So, what was the one on? What was the one on the large conductor to the battery? What was that about?
Don't know.
It should be G4E. Which of the following direct fuse power connections would be best for a 100 watt HF mobile installation? And the answer is use heavy gauge wire because there's a lot of current in a 100 watt radio. Oh, I know. The answer is A, to the battery. You want the power to come directly off the battery, not off the. The point of this is that they want you to connect your radio directly to the battery with a heavy gauge wire. That's the best source of power for a radio. That way, because the alternator goes through some other wires that are inside the car, and therefore you're going to create other impedances going on. So the battery is the best place to connect your radio. That's what that one's about. Don't plug the radio into a cigarette lighter thing. That's with the auxiliary power socket. That's the old lighter. Don't do that. That's not even close for 100 watts. It's like 8 amps of current. That'll either make the radio not work or the fuse blow.
Oh, I bought a special cord to plug my 5 watt handheld into the
5 watts. Okay, 5 watts. Okay.
Alrighty, thank you.
100 watts, not good.
No. Okay.
In fact, I wouldn't even on a 5 watt radio that's got a battery in it. I would just run off the battery. I wouldn't even run off the car. And I would put an inverter in the car and just charge the battery when I'm not using it.
Okay.
But that's just me. Okay. Almost anything electrical can cause radio interference. So that was why all those things were important.
Yes.
That's my point about the fuel thing. The fuel delivery system creates a lot of transients. Okay. So let's go to alternate power sources. Photovoltaic conversion is sunlight to electricity. Pretty popular these days. The thing that nobody knows is open circuit voltage is about 0.5 volt. So if I have a solar cell, one solar cell, not a panel, one solar cell, and I don't connect anything to the cell, just sunlight, I'll get about 0.5 volt on that one cell. Okay, so a series diode, a diode just stops current from going one direction to the other. So if you put a series diode in, the photovoltaic cell will charge the battery. But if there's no sunlight, the battery might force current into the photocell. So they usually put a diode in there so that you can't have the current go into the photocell when there's no sun.
Got it.
So if the sun isn't shining, you put, to protect it, you put a diode. That's what that question's about. And I don't know, this wind power thing was out of the blue. This goes back to the old days of wind power, I guess. But what was that one? That was What's the disadvantage of using wind? And the answer was you might need a storage system in an emergency because you might not have wind. Well,
Yeah.
you might not have sun either. Try doing this at night.
It's the same thing for solar.
I'm going to bet you that this question changed on the new, this question changed on the new thing, because there's no reason why wind power wouldn't be just as good or better in an emergency system. That's not really a disadvantage. It's a disadvantage for everything that doesn't give you power all the time.
Mm-hmm.
Right?
Yeah, right, exactly.
So I think that's a stupid question, but that's okay. All right, it's now 20 of 9, guys. I'm really just getting to this signal and emission stuff, and I think let me just look quickly here. There's a lot of slides here. I don't think I can do justice to this in the next 10 minutes.
No, I'm not sure I can absorb it.
Yeah, I mean, I think I'm pushing it. You know what? We might end up having to catch up on a couple of these things on the last Friday, just review questions. So look over the slides and and let me know if you cannot get to the 2023 seminar Dropbox, because I might send a link out tomorrow because I know the link goes to the public directory, so it should be in there. I think you should have access to this slide presentation. I'm going to save it and put it back up there in a minute before tonight. Yeah, this is a real heavy topic. So I'm going to pick up here next week, okay? And I'll try to be a little faster on the propagation. Next week is on let's see, this is 4, right? 5 is on propagation, and 6 is sort of a wrap up and try to cover anything I forgot to cover or didn't cover. So next time we'll talk about, I'll pick up from here, and I will, and we'll talk about radio propagation, reflections and delays and all those things related to propagation. I'll stop here, and if you have questions, I'll be here for another couple of minutes. Otherwise, I'll kill the sessions. We can all go do something else.
Wait, what? Just one quick question, Paul.
Sure, yeah, you can ask all the questions you want. Oh, go ahead.
What time do we need to be at St. Barnabas on the 22nd?
I believe it's 10 o'clock. We used to do it at 9, but Mike's moved it up to 10.
Okay, good. That's better.
So I would get there at 15:15.
Okay.
And we're usually ready by 15:15, and you can start anytime when you get there. And if you're late, don't not come, because we'll be there for at least an hour and a half. So
okay.
And there's no time limit per se. So we'll stay with you until you finish.
Okay. Very good. Thank you.
I think of this.
All right. Well, thank you, Paul.
Okay. Well, you guys seem to be catching on here. I didn't do it by the questions because I didn't want to make it too boring, and I wanted to kind of give you some insight around the questions. Right. If you just want to look at, why an answer is the answer, you can go to that other website. Ham Study has usually enough stuff to satisfy you as well by looking at the little tab on the Ham Study question.
Right.
If you have a weak area that you really want a little bit of bolstering on, I'd be happy to do a separate thing. If you need a little bit more time in an area and it, let me know. I can always do another extra little thing. I mean, I'm not hung up with that, but I'm trying to do something formal here to give you a guide, to give you a guide as to how these things relate. Okay.
Sounds good.
Sounds good.
I'm glad I had all my little toys tonight. I got
No,
my
that's
reflector,
helpful to see what those.
field strength meter. These things are real practical things. I mean, they're things that you can use in a Radio Shack to quite good effect. The VNA is one of the instruments that has historically been poorly represented in radio among amateurs. And I'm trying to make it available to everybody because it's actually, today, it's like, an oscilloscope by far is the most useful instrument that I've ever seen, ever created. I mean, you use it to do anything. But outside of that, for measuring antennas, standing wave ratio, filters, all that stuff, a VNA is like the magic thing. And a lot of people don't get to touch them unless they're graduate students in electrical engineering. It's crazy. I mean,
Wow.
It's the most practical instrument around, and they've been using these crazy little directional watt meters to measure standing wave ratio, which tells you absolutely nothing about the reactance of your antenna. So I mean, yeah, they're handy, they're simple, but they'll tell you half of the story. A VNA gives you the whole measurement, and it's just a good instrument to have. And now you can buy them for $60.
No kidding. Wow.
I mean, these things used to be $60 or more, and everybody had one. Well, for $60 now, you can buy a 1 gigahertz vector network analyzer in a little box like this. So why would you buy this? maybe to show it in class. Like, here's a directional voltmeter. I don't know. All right, have fun, guys.
Okay, thank you.
I will be away next week, but I am on email. So don't. If you have something, send me an email. I'll reply.
Safe travels.
Yes, have fun.
Safe travels.
Okay, I'm off to see the grandkids.
Love it.
Enjoy.
Bye. Thank you.
All right, bye, Robert. I don't know if. All right, I'm going to kill the meeting here somehow. Stop the recording.